Hi guys. Okay, so now we are going to look at the periodic table. So what is a periodic table? First of all, periodic table is the arrangement of elements. There are about 118 elements that are known to us, and they are arranged in a certain pattern, which we will discuss in this video. And what are elements? Elements are the purest substances which contain only or which are made up of only one type of particles. Let's say, for example, here, copper. Copper is made up of only one type of atoms, the smallest particle that retains the physical and the chemical property of this substance. That's the atom, that's considered to be atom, which is the smallest particle. Okay, so this copper is made up of the same kind of particles, and every element is associated with some physical and chemical properties. So what are the physical properties of copper? Physical properties of copper are that it's brown in color, it's shiny, it is hard, it can be made into wires, it can be beaten into thin sheets, right? And it has a very high melting point and boiling point. As you can see on the screen, the melting point is 1084.62 degrees Celsius and the boiling point is 2562 degrees Celsius. Okay, so these are the physical properties. So the physical properties, as we discussed in one of the previous lectures as well, are based on how a substance looks, how it feels, how it tastes, how it smells, and how is it to touch. So you can make out when you touch copper, kind of just by closing your eyes, that it could have some kind of a metallic, it has a feel to it, because the kind of sound it will make if it falls, ting, 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 and then it's hard and it may be a little bit, shiny and smooth. So those things. Okay. Now, other thing is, those are the physical properties. Now, chemical properties, whenever copper reacts with something, for the most part, copper produces a blue colored, compound. So when copper mixes with, let's say, sulfate, so that is going to be a copper sulfate. It's very crystalline, solid, and it has blue color. And I just want to always, connect things outside of the book. So if you have seen, or if you know about this, this is the lake, the Oregon. This is a lake, Crater Lake in Oregon, and the blue color is because of the copper salts that are present in this lake. And it's very pure, it's very dark, rich blue color. So that's coming from copper, okay, copper salts. So we see that, let's look at the other examples of some of the other elements. For example, let's say everybody knows gold, okay? So gold, everybody knows it's shiny, it's hard, and we make obviously jewelry, and like it has a very high boiling point, very high melting point, and it does not, for the most part, react with many things. So it's very least reactive. Okay, so this gold can be used, because it can be made into thin sheets. So gold can be used for electroplating also. Okay, so this jewelry you can plate it with gold and make it like, make it look like gold, although it may be silver or some other base metal. Okay, so that is the properties of gold. And again, this is an element that is put in a periodic table, and there is a reason why gold is placed here. There's a reason why copper is placed on top of that. Okay, but now we're going to look into the placement a little bit later. Just let's look at some of the properties of the elements that are found. And so here, oxygen. So yes, we cannot see oxygen, but when oxygen is liquefied, it's a blue colored, it forms a blue colored liquid. And again, if you look at the melting point is negative because it's in a gaseous state at room temperature. At gaseous, it's a gas at room temperature, so it has to be liquefied at a very low temperature, and then it has to be further, if it has to be solidification has to be done at an extremely low temperature, which is negative 218 degrees Celsius. And again, that solid oxygen is going to, if you liquid oxygen, if you boil it, then it will be negative 186.9 degrees Celsius. At that temperature, it begins to convert from a liquid state to a gaseous state. Okay, so density, again, 1.429. Okay, so this is the the density of oxygen. And oxygen, portable oxygen bars, and bowl of liquid oxygen is right here, and this is on the arc tubes and so forth. So other, oxygen tanks, all this oxygen is used for those purposes. So applications. Now let's look at, there are only two elements that are liquids. So here is this bromine, now very toxic, okay, but if you look at the melting point, negative 7.3. So this means that below zero, it has a melting point. So that means at room temperature, which is 25 degrees Celsius, this is going to be vaporizing. It exists as a liquid state, but at the same time, it is always vaporizing. Sorry about that. Sorry about that. Okay, next, the boiling point is 59 degrees Celsius. So that's bromine. So bromine is used, in like, for the purposes, flame retardant, it's used there, or it is used for pool tablets, or in the Mountain Dew, the vegetable, the vegetable oil. There was brominated vegetable oil that was being used in this soft drink. Okay, so these are again just a basic introduction of all these elements and how they are found either in their natural state or in a, in either in the combined state or uncombined state. This is iodine. Now, iodine is subliming at room temperature. In other words, from a solid, beautiful crystalline state, it converts to vapors, purple colored, violet colored vapors. Okay, and this iodine is the one that is used as, for like a tincture of iodine with alcohol that's used for, swabs. So in the medical, field for your cuts and wounds. Okay, so that's for the iodine. Next, let's look at a few others. Let's say, for example, um, let's say titanium. Okay, so you see density of titanium 4.5, so that means it's very heavy. So the moment you put it in water, it is going to sink. Melting point is very high because it's a solid. It has to be heated at a very high temperature, so it would convert from a solid to a gas liquid state. Boiling, again, once it's liquefied, then it boils at 3287 degrees, so very high temperature. It's going to be converted from a liquid to a gaseous state. Okay, so here we have all this interesting uses of titanium pen, and it's pretty expensive though. So gas phase titanium crystals, shiny vaporized, deposited titanium crystals. So these have been, made, and then we have, look at this, the baby of the the most abundant element in the universe that is beyond the earth crust is hydrogen. Hydrogen is responsible for the birth of stars, so the beautiful planets and the stars that you see in the skies, this is all the work of hydrogen, fusion reactions happening. So this hydrogen, again, it's um it's a colorless gas, and they create these spectacular sights. So this is the Eagle Nebula. This is, I think these are the pillars of creation, a very famous photo from NASA. Okay. And so this is a fusion reaction happening in the sun. So the light that you get on this earth, the heat that you get on this earth is actually a fusion reaction happening in the sun. And we are now looking into, how we can mimic the power of the sun on this earth. This is happening in these, nuclear power plants where we are trying to use the fusion reactions. We have generated hydrogen from the water on this earth, and we're trying to fuse it and then trying to see if we can mimic the power of the sun. And on a beta scale, that has been done at the Torres experiment laboratory in, I think it's in Italy. And we're trying to look for alternative energy source. If hydrogen could be, one of them. Okay, so if that happens, if fusion reactions, we're successful in, providing the energy using the fusion reactions, then the world is going to be very different. One bucket of water is all that is needed to suffice the energy needs of a human being for, you know, 30 years. So that is, at least that's the projection. Anyways, so that was a basic introduction to the elements, their physical and the chemical properties and how they look in your welcome to explore this. This is the photographic periodic table of elements. Now let's look at the dynamic one. Now this is more. Now I want you to focus here. Look at this. I'm going to just Okay, so I want you to look at this periodic table. This is again the arrangement of the elements. And now we're going to just break it down. Those elements is a very broad term. Every element is made up of atoms. So this is really the arrangement of atoms. So every atom, if you look at it, let me put it here. Every atom right here, as you can see, there is a symbol on every atom has a symbol, right? Every atom has a symbol. Hydrogen is H, lithium is Li, beryllium is Be, boron is B, carbon is C, nitrogen is N, oxygen is O, fluorine is F, neon is Ne, and so forth. Okay, so there's a separate video in which these symbols and the namings have been explained. So you will have to memorize at least the important, symbols and the names. And you can leave the lanthanides. These are the lanthanides and actinides, but at least you should know all these top ones, the names and the symbols. Okay, so that's one thing. Next thing is we're going to look at now that every element is actually having, or every atom has two numbers. One number is on the top and the other number is at the bottom. So let's see if I can get this better. Yeah, right here. So every atom has two numbers. The number on the top is the atomic number, and the number at the bottom is the mass number. Okay, the atomic number is the number of protons, and it also means the number of electrons. And the mass number is the number of protons plus the number of neutrons. Okay, so mass number by mass means the atomic weight. It means like how heavy is this atom? So it is very light. It's the lightest one. Okay, it's a baby of the periodic table. So lightest one. Okay, now here's an interesting part. This hydrogen just by itself with one electron or one proton, this number, the mass number, this is, and we're going to talk about what the protons, electrons are, but the mass number is 1.008, which is the atomic mass units. And that is the number of protons and the neutrons. That's the weight. But the atomic number is the number of protons, and it is the number of protons that determine the identity of the atom. So here we see is the hydrogen with one atom, one proton, very reactive. Now you add one more proton to it and it becomes helium, least reactive. So the identity changes. Okay, you add one more proton to helium. Helium is a gas, you can't see it. You add one more proton to it, it becomes lithium. And what's the deal with lithium? It's a solid and it's very reactive. Helium with two protons was not reactive, but lithium with three protons is so reactive that we have to put it under the oil. Okay, next is beryllium. Look at beryllium. Beryllium is kind of like a base earth element. It's like what do you call, like mud, kind of like that kind of feeling. Okay, so it's not very it's like a mud or a chalk, like it's not very shiny. Okay, so that's beryllium. Anyways, solid. Next, you add 5 protons and it becomes boron, and boron is shiny and solid. Now you add one more proton, 6 protons, it becomes carbon, which is like a black colored, like a rock or like a coal, solid. And one more proton. Now here's an interesting part. Carbon with 6 protons, you can still see a black colored charcoal, right? But you add one more proton with 7 proton, it vanishes in the air. That's nitrogen. And one more proton, it becomes oxygen, which is our life force. One oxygen gas. One more proton, and that's a toxic gas that's going to kill you. So if you breathe in fluorine, that's going to make you very sick. So 9 protons is going to make a toxic gas, but 8 protons is the one that's giving you life. And 10 protons makes neon, which is kind of neutral, and it doesn't react. Okay, so this is non-reactive. Then comes sodium, which is neon with the 10 protons is a gas you cannot see, but you add one more proton and it becomes sodium, which is again solid, very reactive, and you put it under the oil. Okay, so it doesn't, it doesn't catch fire. Next is magnesium. Yeah, it's kind of like grayish colored, metal, and it has solid, of course. Okay, then aluminum, on the other hand, with 13 protons, is quite shiny. We've seen aluminum foils, right? And then comes silicon, and then comes phosphorus, and then comes sulfur, right? Sulfur with its 16 protons is solid, but chlorine with its 17 protons is a liquid, is a gas, I'm sorry. Okay, is a gas. And then comes argon, which is with the 18 protons, not non-reactive at all. Chlorine is highly reactive. Chlorine reacts to its own self, but argon, non-reactive. So you see, one proton changes the identity of the atoms, and these atoms then, they form a it's a new atom completely just by changing the proton. So what are protons, electrons, neutrons? We will discuss that more in the next chapter, but in a while. But let's look at um, the arrangement. Now, here's another thing. Look at this: hydrogen 1, helium 2, lithium 3, beryllium 4, boron 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, neon 10, and then. So there is a reason why, we go all the way from 1 till 18 only, and why we don't, why don't we keep going further? Why can't we put it in one straight line? There is a reason. And that is that, here's the thing. Each and every element, their goal is to look like a noble gas. And what is a noble gas? All the noble gases are here. So their goal, they all want to be like a noble gas. And when they want to be like a noble gas, it means that they are going to, either lose electrons or they gain electrons. So all their chemical reactivity, all their chemical behaviors is driven by internally, their wish is to look like a nearest noble gas. And this noble gas could be either the one which is right next to them, or it's one above the rows. And so so you see this number right here. This is the row. So row number 1, or it's also called period. And this also depicts the energy level. So this one has 1 energy level. This has 2 energy level. There are 3 energy. All these atoms that are in this row will have 3 energy level. All the atoms that are in the 4th row, 4 energy levels. 5 row, 5 energy levels. 6 row, 6 energy levels. 7th row, 7 energy levels. Okay, so forth. So next is, you see these numbers on top. These are the group numbers. So this is group number 1, group number 2, and then hold on to this one right here. This is actually 13 actually means group 3A. This is group 4A. 14 is 4A, 15 is 5A, 16 is 6A, 17 is 7A, and 18 is 8A. Okay, so these are like the representative elements. So more common, on this earth. Now, again, another type of grouping is based on their chemical behaviors. They are arranged in the order of their chemical behaviors, the chemical reactivity. And the chemical reactivity increases as you go down from top to bottom. So in other words, lithium, okay, reactive, sodium, more reactive, potassium, even more reactive. So the chemical behavior is still the same. If you take lithium, you drop it in water, it will make this sound shh, and that is, it is making lithium hydroxide and it's releasing hydrogen gas. But you take sodium, you dump it in water, yes, it is also going to produce shh, but it's going to be a louder shh sound. And then that hydrogen is also released and it jumps in the water. But the moment you drop potassium in water, huge, loud, explosion with purple colored, violet colored lights, right? And it produces also hydrogen gas, but instantaneously. So the speed increases of the reaction, but the behavior is the same. The intensity increases. So anyways, so these elements that are in group 1A are also called alkali metals. The elements that are present in group 2A are called alkaline earth metals because they all behave the same way, right? And yeah, some of them may have like more or less the same kind of physical properties that, they're not very, like all these guys over here in group 1A are so reactive that, they have to be placed under the oil. Okay, these guys are kind of like, not very shiny, but still solid, still metallic in nature. Okay. Now, um, I'm talking about metals. Now we are talking about metals first of all. So all these elements are metallic. Now, what are metals? Metals are those that are shiny, different variations in shine also. They make that metallic sound when they fall down. They are solid, and they are good conductors. Most of them are good conductors of electricity, good conductors of heat. Okay, they all have very high melting points, they have very high boiling points, and they readily react with non-metals or other polyatomic ions, to form salts generally. Okay, so these are the basic things about metals. So ductility, these mean they can be made into wires. Malleability is that you can braid them up and they can be made into thin sheets. So that's malleability. Okay, so these elements that you see on the screen are all metals. Now let's continue with this. So alkali metals, alkaline earth metals, then comes the lanthanoids, which are these elements that are present, these are rare earth elements. Then comes actinoids, again rare earth elements. Then comes the transition elements. These are the ones that are in the middle, transition elements, the pink ones. Then the post-transition elements. And then comes the metalloids. The metalloids are in between the metals and the non-metals. So they are conductors of electricity, but not as strong as the majority of the metals are. So like partial conductors of electricity, partial conductors of heat. This is why silica is being used, in the semiconductor industry, because semiconductor means they conduct electricity, but semi, like partially, like that. Just good enough for us so that we can have our computers and, other electronic devices. Okay, so anyways, now look at the non-metals. So there are two non-metals. You see the one that is in the green boxes and the other in the pink boxes. So pink boxes are noble gases. All of them are noble gases. They are not reactive at all. They don't react. Okay, you can make, see, here's another thing about chemistry. You can change the reaction conditions, and yes, you can make things react. You can force them to react. But ordinarily at room temperature, when we talk about in standard conditions, they don't. Then comes the reactive non-metals. Now here, fluorine, chlorine, bromine, iodine, they're so reactive that they react to themselves. Oxygen, so reactive, reacts to itself. This is oxygen. Then comes the nitrogen, reacts to itself. Carbon is a non-metal. Okay, so now what is the difference between the metals and the non-metals? Like broadly, non-metals are not going to be good conductors of electricity at all. They do not conduct electricity. If you beat the metals, yes, you can make them into thin sheets, but you take a non-metal, you beat it up, it's going to shatter. Okay, so that is a difference. Non-metals exist, like fluorine, chlorine, bromine, iodine also sublimes, and then all these noble gases, they exist as oxygen, nitrogen, they exist as gases. But all the metals exist as liquids. Now, there are some exceptions to it. Look at this. Helium, mercury and bromine. These are the only two elements that are liquid. Only two. So one is mercury, mercury is Hg, and then there is a bromine, which is liquid. Again, this is a liquid. Okay, so mercury, on the other hand, they are placed in different, or just because they are liquids, it doesn't mean you have to place them in the same column. They are placed in these different boxes based on their chemical behaviors. Okay, so this is one piece right here. Next thing that you're going to see is, just give me 1 second. Okay, I'm going to just show you from the book. All right, so now we are looking at the periodic table, which we just now discussed is. So in this, the types of elements, if this is just a pictorial representation of the elements. So you can see the metals are like, placed, are very broad, they have more metals in the periodic table. Then the non-metals are all the green ones right here. And then the step ladder, these are the metalloids. Okay, so this is one piece. So this is how, the periodic table is basically classified. based on these. Now, there's another thing is the special names for the sections in the periodic table. So the alkali metals, the group 1A, alkaline metals are group 2A, and then halogens are group 7A, then the noble gases are group 8A, okay, the transition metals are in the middle, and then the lanthanides and the actinides, okay. So this is another way you can, group by grouping these elements based on, again, their similar chemical reactivity. Now, there is another piece in the periodic table, the way they are arranged. And again, we see a very interesting, perfect, pattern. So before we look into this, actually, let me just walk you through this piece. Okay, here is this periodic table, and let's see if I can make it a little bit bigger. Okay, here is your periodic table. And as you can see that we talked about, these are the periods or the rows, and these also represent the energy levels. So row number 1, row number 2, row number 3, row number 4, 5, 6, and 7. So there are, 7 energy levels here. That's one piece. Secondly, this one number you see, this is group 1A. This is 2A. And here actually 13 is 3A, 4A, 5A, 6A, 7A, and 8A. And remaining, these are these transition elements. They are different. Now, there's another thing here. This also means that all these elements here will have, all of these atoms will have one electron in their last shell, in their last energy level, one electron, one valence electron. So the last electron that is in the energy levels in an atom is called a valence electron. So this is the valence electron, one valence electron. This has two valence electrons. So hold on to these. The transition elements, generally they are, considered to have two valence electrons, but there's always exceptions to the rules. Hold on. Okay, so just look at this one. This is 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, and 8 valence electrons. So we put them as 1, 2, 3 all the way till 18, but really this is 1A, 2A, this is 3A. So just make a note of it: 3A, 4A, 5A, 6A, 7A, and 8A. And all these elements right here, these guys, all of them will have the same number of valence electrons in their last shell. Okay, so that's one thing. Now, where are those last electrons ending? So that depends on their last, orbital, in which orbital. So if they are we're going to study this in a minute, and when we talk about electronic configuration. So I hardly recommend that after you study the electronic configuration, if you got a more grasp of it, go back and look at this, then you will understand this more. But anyway, so here, starting from here, the last electron is found in 2s orbital. So here 3s orbital, 4s orbital, 5s orbital, and 6s orbital. So all these are, the s orbitals are the last orbital, the valence electrons, where that valence electron is found. And so these are valence electrons are found. So these are basically all of them, the electrons are ending in that S, so they are called S block. So this is S block. The last electron, valence electron, ends in D orbital, so this is D block. The last electrons are ending in p orbital, so this is p block. And then the last electrons are ending, or the valence electrons are found in the f orbital, so they are f blocks. Okay, so this is another way these periodic tables have been arranged based on the blocks. Okay, now so there's another very interesting thing that I want to show you about the periodic table. Here is your periodic table, and we see one more time, S orbitals can hold a maximum of only 2 electrons. Okay, so all these elements that are present or in group 1A, their last electron is going to end in S orbital, and there's only going to be one orbital. So it will be S1, their last valence, their valence shell electrons. These are going to be S2. So this is 2s2, this is 3s2, this is 4s2, 5s2, 6s2, and 7s2. So all these elements, though, so the numbers 1s2, 2s2, 3s2, 4s2 represent the energy levels or the periods. And then these electrons that are in the valence shell, they correlate with the group number. Okay, now this is the D block. So all of them are going to end in D. Next is this and something else also in the D. I'll show you in a minute, but look at it. P orbitals can hold a maximum of 6 electrons. So with that said, how many columns do you see here? 1, 2, 3, 4, 5, and 6. See that? Now, interesting thing is here that P can hold 6 electrons. So this is going to be P1. All these elements will have P1. These will be P2. This will be P3. This is P4. All of them P5 and all of them P6. Okay, that's one thing. Next is similarly, now you can make a prediction for the D. D holds a maximum of 10 electrons. So how many columns are going to be in the middle of the periodic table? 10. D1, D2, D3, D4, D5, D6, D7, D8, D9, and D10. Okay, so in other words, the valence electron here is only going to be one valence electron, and it is present in D. 2 valence electrons in D, 3 valence electrons in D, and so forth. Okay, so ideally it's not even like, valence shell. The real valence shell is this for the case of D blocks, but we will look into it in a minute. But look at these similarly, the lanthanoids and the actinoids. F block should have 14 because F can hold a maximum of 14 electrons. Okay, now here another point that we need to make, and that is that now very important. So this is 1s, this is one first row, one energy level, second row, this is the third row, but this is the fourth row, which is fine, but from this is actually 3D. So 3D, so this is 4s, this is 4s, okay, S block 4s, but it starts from here 3D. And why is that so? It relates to the electronic configuration, which means that the energy levels are quantized. In other words, the energy levels are, there's a certain value of the energy. So 1s is a lower energy level, 2s is a little bit higher, then comes 2p, a little bit higher, then comes 3s, fine, a little bit higher, then comes 3p, which is a little bit higher energy level. But after 3p, we would expect 3d, but 4s2 comes. 4s2 is a lower energy level, no lower energy, higher than 3p, but lower than 3d. So that is why 4s2 comes first. And then there are like so many other reasons for it: penetration effect, shielding effects, nuclear pull, nuclear, attraction. All those things are responsible for all these differences in the energy levels. So what we see that the structure of atom is, yes, it's like we would think it to be like a solar system. Sun is in the middle, and outside are these energy levels, and these energy levels have like certain value to it. But after some time, the further away you go from the center, from the nucleus, right, the further away you go, further away, then these energy levels begin to overlap, because of which, there is the 3D is higher in energy level than 4s. So this is why this is the 4s block, and then this starts from 3D, and then once you come here, this is 4p. Similarly here, this is the 5s, but transition element, this thing is 4D, and then comes the 5p. Now here, lanthanides, from here, they start from here, 56, after that is the lanthanides, and then the 88 is the actinoid. So these F block elements are going to start from here, and then they go all the way till like 70, and then comes the 71, 72, and so forth. So this piece, we have to pull it out, and brought it in the bottom. First of all, they're rare earths, so they're not very common. And secondly is that we would be dealing with a periodic table that is very much stretched out. So this is the reason why this lanthanides and actinides, these guys right here, we pull them out, and we look the periodic table on like the most important and the abundant elements. Okay, so this was the introduction to the periodic table, and I hope it was easy. We are going to discuss this more, but this is a backbone, and I highly recommend one thing. It's very important you start memorizing the symbols and the names. Okay, thank you.